function. The purpose of this lab is Faraday's law relates time-varying magnetic field to a Curly electric field, whose path integral around a closed path is not zero but provides an EMF that can drive current. This current in turn produces a magnetic field that exerts a force on the source of the external magnetic field. In this lab, the source of that external magnetic field is a falling bar magnet, and the induced current is driven in a tube of aluminum foil. The interaction between the falling magnet and the tube of aluminum foil produces an interesting result, which you will explore in this lab. However, in our experiment, we did not use a tube of aluminum foil, we used a copper tube. Fundamental physical principles used: Faraday's law, force of gravity near Earth's surface, and Biot-Savart law. Computational model used: create a computational model that simulates the falling of a bar magnet through a metal tube and creates a velocity time graph of the falling magnet. Assumptions made: assume the resistivity of the tube to be 2.65 times 10 to the negative 8 ohm meters. Assume the bar magnet to reach terminal velocity while in the tube. Assumed air resistance to be negligible. Preview of results. In real life, the magnet consistently took about 3 seconds once entered to exit the tube. In the computational model, the magnet took 3.781 seconds once entered to exit the tube. This is pretty close to the around 3 seconds observed in real life. Experiment and calculations. Here is a photo of our experiment. This little magnet at the top is the system, and the surroundings are everything else. Once the magnet is dropped, it causes a change in the magnetic flux of the cross section of the tube, and this change in magnetic flux induces a EMF that circles around the direction of the change of magnetic flux. And since this copper tube is a conductor, this EMF causes the mobile electrons to move, and thus a current is induced. This induced current, which is a loop, creates a magnetic dipole in and of itself, and the two magnetic dipoles, the one that's literally a bar magnet and the one that is induced by the current, interact, causing the bar magnet to fall at terminal velocity, as the force of the two magnetic dipoles acting on each other cancel out the force of gravity acting on the bar magnet. Code. Here is the part of the code in which the function was defined to calculate magnetic flux, or the change of magnetic flux. And here is a screenshot of the output of the code animation. As you can see, there's a little bar magnet that has made its way fully through the tube. And here is the velocity versus time graph. Discussion and conclusions. Interpreting the simulation. The magnetic dipole moment points in the positive y direction, meaning the magnet is going into the tube south end first. This means as the magnet falls, the change in magnetic flux below the magnet is also in the positive y direction. This induces a clockwise current below the magnet to create a magnetic field to counteract this change in flux. Red is clockwise and blue is counterclockwise in the computational model. On the macro scale, the dynamics of the system do not change when the magnet is flipped. Flipping the magnet causes the direction of the induced currents to flip. The computational model could potentially be made more accurate by using actual integrals to make magnetic field calculations. Similarities and differences. In real life, the magnet consistently took about 3 seconds once entered to exit the tube. In the computational model, the magnet took 3.781 seconds once entered to exit the tube. This is pretty close to the around 3 seconds observed in real life. Velocity versus time plot. The velocity versus time plot of the computational model shows that in the model, the magnet experienced a net downward force while not in the tube. This is evident by the fact that it accelerated when it was not in the tube. In the tube, however, the magnet did not accelerate, meaning that all forces in the tube, while the magnet was in the tube, on the magnet cancel each other out, and the magnet fell at terminal velocity. Possible sources of error. Any of the assumptions made for this experiment were not true and led to a significant difference in the results. Rewind video to the assumptions made section for more details. Error in coding, human error when conducting or collecting data of the experiment. What if? If the resistivity of the conductor were reduced to as close as possible to zero, the falling magnet would stop while in the tube and levitate. If holes or slots were cut into the tube, this would decrease the magnetic force acting on the magnet that is canceling out the force of gravity. This is because these holes would prevent the induction of current loops in the parts of the tube with these holes, because while the EMF would still be induced, there would be no conductor for these mobile charges to move around through completely in these complete loops because there's holes in it. Thank you so much for listening. Have an awesome